Have you ever wondered why you don't have any cell phone reception inside of large skyscrapers?
Or do you wonder how metals behave in the neighborhood of magnets and magnetic fields?
My name is Bouke.
And I'm Nick.
We both study applied physics at Eindhoven University of Technology.
This is part 2 of a video short in which we're going to explain various concepts in physics. This episode is all about external electric fields and Faraday's cage.
Welcome to one of the main lecture halls in the auditorium building on the campus of the TUE. Usually this lecture hall is filled with students watching an interesting lecture, but today we're going to use it for a fun experiment. Next to me here we have a big metal ball. This metal ball functions as a Faraday's cage. This means that if you're on the inside, you can safely touch the outside walls without getting shocked. Even if there's a large current on the outside. For very good Faraday's cages, can also block out electromagnetic signals. This means that if you're on the inside you can't get any cell phone reception. We are, of course, going to test this, but first we need some theory.
We have introduced the concept of a Faraday's cage a couple of times. But what is it exactly? Well, a Faraday's cage is just a type of metal ball. And in the metal there are charge carriers. These charge carriers can be seen as mobile electric charges that can be moved by an electric field. Well, when we impose an external electric field on the Faraday's cage, the mobile charge carriers inside them experience a force induced on them by the external electric field, according to F is Q times E. This results in a charge distribution across the metal ball, as the negative charge carriers will move to one side, while the positive charge carriers will move to the other side. The exact distribution of the electric charges depends on the type, shape and direction of the electric field, but generally it will be the case that one part will become positively charged, while the other will become negatively charged. This introduces an internal electric field that opposes the external electric field. This has the effect of finally reducing the voltage inside the metal cage a lot. It lowers it so much that you can just safely touch the inside of the metal sphere without getting shocked. We have also introduced the concept that a good Faraday's cage blocks certain types of electromagnetic radiation, such as radio frequencies or the frequencies used by your cell phone to get cell phone reception, 4G, just internet in general, Wi-Fi. How good the Faraday's cage protects against certain types of electromagnetic radiation depends on the mesh size, the grid of wires that makes up the Faraday's cage. A good rule of thumb is that you need a mesh size that is about 10 times smaller than the wavelength of the radiation that you want to block. This is why, when you are in certain high old buildings filled with wires, metal pipes and other things, that when you are on the lower levels you won't get any good cell phone reception, because the building itself acts as a type of Faraday's cage. Well, now that we know the theory, we can finally put it to the test.
So, now for the moment we've all been waiting for, the experiment. We've put Nick inside of the Faraday's cage and we put around 4 kilovolts on the cage itself. However, there's no electric field on the inside of the cage, and also Nick can safely touch the walls. However, if I do that on the outside, there should be a big discharge. Whew. Now, from that we can conclude that the theory coincides with the experiment, and I guess it's now time to get Nick out of the cage. So Nick, what did we learn today?
Well, we have learned that if we apply an external electric field on a hollow metal cage, the inside of that cage will remain mostly uncharged. Furthermore, we have learned that if you are in a very tall, high-rise building with a lot of wires and pipes inside, the building will act as a cage of Faraday, and thus when you are on the bottom floor, you won't get any cell phone reception.
If you're interested in studying applied physics here at Eindhoven University of Technology, please check the link below.